Hello everybody, in this episode of Programming and Algorithms we're going to look at the complexity of an algorithm. So we call that algorithmic complexity. By complexity what I mean is how long does it take a program to run. So we've been talking about the searching already and the sorting and how different searches are quicker. So we have a whole science in computer science looking at the way we measure how efficient an algorithm is and ways to optimize it. So we looked at some ways to optimize bubble sort. One simple way of looking at it is if we're processing an array, how long does it take to go through that array? And as we saw, the sequential search, if the array is n digits long, it takes n comparisons to get to the end of it, whereas with the binary search, as long as the data is sorted, it takes much less time. For a sequential search, that is where we go one step at a time. We say that the sequential search is order n, so the O notation means approximately how many comparisons will it be. If we go from 0 to n minus 1, that's n comparisons. Even if we went to 0 to n minus 5, we'd say it's approximately n comparisons. So the order, the O in brackets around the n, indicates roughly how many comparisons it'll take. So if in practice, on average, it takes n minus 3 or n minus 2, if we're thinking about 100 million elements of an array, then it's close enough to n not to be worried about it. And as we saw for the binary search, because the binary search takes the full length of the array, then halves it, then halves it, then halves it. If we have an array of, let's say, 8 elements, we'll get that done in 3 comparisons. If we have an array of 1,000 elements, we can get that done in 10 or 11 comparisons. So the mathematical function that describes how quick that is, it's log to the base 2n. So we say that binary search is log to the base 2n. If you want to look up why that is, it's just because we're halving, so it's to the base 2, and we're reducing very quickly how much comparisons we have to do. Because for bubble sort, we have 2 loops, one loop inside the other loop. The inside loop runs, if the inside loop runs, let's say m times, and the outside loop runs n times, then we've m by n comparisons that we do, or if they're both n times, then it's n squared comparisons we do. If we had a loop and then a loop following it, it'd be order 2n. For the loop inside a loop, we say the complexity of that is order n squared. For the insertion sort, where we do the comparisons again, it's the same sort of thing. We have a loop inside a loop, so we said that's order n squared as well. When we talk about the complexity of something using our order notation, or it's sometimes colloquially called big O notation, it's really an estimate of how much on average the algorithm will take to execute the number of comparisons. We can look at worst case and best case as well. So let's say if we're doing a sort, the best case is that the data is sorted already and it'll just take one pass, whereas the average will generally be about n squared. So that's an introduction to algorithmic complexity. We'll look at a lot more in the next semester, but thanks very much for now. We'll see you on the next episode.